Hi everybody, this is Graduate Statistics, University of Cincinnati. This is week 4 and that's video 5. We ended up the previous video talking about measures of spread. And when we talked about measures of center, we mentioned the idea of robust statistics. Statistics that are robust are those that are not influenced by extreme values. So those are the good ones to use when you want to summarize data distributions that are very, very skewed, or substantially skewed, I should say. So median, you already knew, but also interquartile range are more robust to skewness and outliers than mean and standard deviation. Therefore, for highly skewed distributions, it is often more helpful to use median and interquartile range to describe the center and the spread. For symmetric distributions, it is often more helpful to use the mean and the standard deviation to describe the center and the spread. So now let's wrap up with the idea of telling stories with data using descriptive statistics. We started with the questions of what is life expectancy now, how has it changed over time, and has it changed over time and by how much? And the data that we had in our hands were data collected across the globe in the 1900s, in the 1900 year and 2000. And we started our exploration of the data set to transform data into information by plotting a histogram of histograms of life expectancy in these 2 years. Histograms are great. They provide a view of data density. They're especially useful to help us gauge the shape of the distribution, which, as I said, we do for a reason. We do because that's how we decide whether or not we need robust summary metrics like median and interquartile range to describe the data, or if mean and standard deviation, which are the most popular ones, the most powerful ones, can be used reliably. So they are important, but they are not the best ones to tell the story that will be compelling to answer the questions that we have. Although they provide hints already, right? The peak is changing towards higher number of years. So what story these 2 histograms tell, and what kinds of data visualization might tell the story in a more compact kind of way. So given that we looked at the distribution and we found that the distribution was a bit skewed in the year 2000, maybe we want to explore presenting the data highlighting the median, and as spread, highlighting the interquartile range. And in that case, box plots are great. So here is how I would say, if you're asking the question, what's the life expectancy around the globe right now? You can see that this is a nice plot because it gives you the median value, which is right around 70, and the box represents the interquartile range. That's Q3, the 75th percentile, and that's Q1, the 25th percentile. It's also nice because it gives us an idea of the spread of the data within the expected variance range, which the whiskers indicate, but it also shows us the outliers, points that are outside the expected, the tolerance area for spread. And we can see that there is a country, Eritrea, which is a country in Africa, that in 2000 is still showing pretty low values of life expectation, below 40. So it catches attention to that. We can see the extremes of the distribution. And the extreme here is within the tolerance range because you don't see it as a point, which is the maximum of the distribution on the upper side. And if you go back to the data set, you can locate Japan as the country that is at the top. So, with figures, it's nice because you can kind of put a title, life expectancy in the world, a bright picture, indicating that we're not bad as a full group, even though we want to also highlight that there are countries being left behind more than others. You can see how the skew is towards lower values of life expectancy. So hopefully in another century, this is some more, tight distribution right around the high value where everybody's benefiting of the gains in health. Let's just explore a bit more in more detail what the box plot represents. So the box in a box plot represents the middle 50% of the data, or the interquartile range. So the box in the box plot, that's where 50% of the data points are located. And the thick line in the box is the median. So I had told you that. The whiskers of the plot, these guys here, can extend to values in the distribution that go up to the interquartile range value times 1.5. That's kind of the tolerance range. So away from Q3 and Q1. And the max upper whisker is Q3, more precisely Q3 plus 1.5 times the interquartile range value. So that's the maximum. It will go in this direction. So if points are more extreme than that, they will show up as points. The max lower whisker, the max it will extend down, is Q1 minus 1.5 times IQR, and that's the maximum it will extend. And here it extends less than that. You can see how it's shorter than this one because you don't have values that are more extreme than this, right? So this is the lowest value. So if there were more values here, it would extend more all the way up to Q1 minus 1.5 times IQR. It would be equivalent here to computing kind of the mean plus 2 standard deviations, kind of as a tolerance level. So outliers, any observation that is smaller than Q1 minus 1.5 times IQR. You don't have anything smaller than that on the downside, but anything that's larger than Q3 plus 1.5 times IQR are also typically referred to as outliers. They're points outside of the expected range of variation of the distribution. But of course, this is not something to necessarily delete from the data set because, it's useless information. Sometimes, like in the case of life expectancy, it's pretty useful to know that some countries are staying behind. That's what they're not errors necessarily that you can just drop. You have to think carefully if this is actually a true value in your distribution that needs to be considered in thinking about your data. Now, the other question that we had was if life expectancy around the globe is changing over time and by how much. So we can actually create box plots side by side if we use our categorical factor explanatory variable in the x-axis. So here we have the 1900, here 2000, and we can see how it increased. See the median increase as we had discussed. And we can even see that Eritrea, even though is an outlier on this distribution, it's still above the median, even above the interquartile range of the distribution in the 1900s, right? So it was above the 50% range. So it wasn't up; it would be on the upper range of that distribution. So pointing to the progress, which is nice. We can use also bar graphs. So bar graphs typically are great for mean and standard deviation. So better when you have symmetric distributions. Here we don't have a very large skew, so it would be acceptable to use mean and standard deviation. You can notice that, here is the mean for life expectancy in the 1900s. That's lower than the mean for the 2000, and that's the standard deviation, that's the spread. You can notice very easily that the difference between the 2 years kind of surpasses the variability. This is bigger than the variability within the years, which is a good indication that this will be statistically reliable. We'll come back to that, but it's just a teaser, right? Because this is just a description. We need to know eventually if differences of this size are likely if only chance is at play. And then line graphs you can also create. And that's again the mean and standard deviation. The mean and the standard deviation, you're showing the easily indicating the upward trend in this variable over time. So in the lab, you will work to create all of these plots that you're seeing here. And I'm going to help you understand how you can play with colors, how you can play with the shapes of these little markers. We'll learn how to create both bar and line plots, both, so that you have some experience, some more experience, detailed experience with plotting with ggplot. Now, do I expect you by the end to have that figured out and now from now on you're going to do it alone? No way. We're going to keep reminding you as we move along the course and explore various data sets. You will be a person that will be trying out, being exposed to different data sets, doing the description, and then the inferential statistics right after. So every time we're going to think together what's the best representation for this situation so that you can start making decisions about that. And we always will be recurring with repetitions of the code. And then at some point I'll be slowly removing such that you have to go find it, but it will be a slow process. So I want you to just enjoy this like as an exposition to these things. Don't take these labs so seriously that everything you're, oh my gosh, I'm not going to know how to do this in the exam. Oh my gosh, it is just not helpful. Please take your time, enjoy, just make sure you're trying your best to understand what it is right there in front of you without thinking about what's going to happen in the exam. You will be prepared for this exam. I'm committed to preparing you to this exam. This is practice that is sufficient for this exam, right? A lot of people just like you have taken this class successfully just by taking the time to do these steps, okay? So there's one more video. I'll stop here. There's one more video that I want to show you in order to explore a little bit reasons for what we're seeing, reasons for this trend. And I'll give you some data to figure this out. See you then.